Auzu billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Now we have the next theorem. Every infinite set has a countable subset. For this proof, we will take two sets. Let A is a given set which is infinite. Then we are to prove that A has a countable subset. Let B is a subset of A such that B is finite. Since we know that every finite set is countable, so B is countable. So the result is proof. If B is countable, then our result is proved. Now again, since A is infinite, so choose A1 belong to A, taking as an element. And since A is infinite, so A minus A1 is also infinite, because if we take one element from an infinite set, it is also an infinite set. Therefore, we can choose A2 belong to A minus A1, taking second element from an infinite set. Again, A minus A1 A2 is infinite. There we can take another element, third element A3 belong to A minus A1 A2, containing two process. We can have B is equal to set A1 A2 A3 dash 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 and so on, which is infinitely countable, because we can find a function f from n to b defined by f of n is equal to an, which is bijective 1 1 and onto. From the shape of the function, the given function is bijective and B is a subset of A. So all the elements of B taken from the set A. So we have proved that, thus we have proved that every infinite set has a countable subset. Now we have next theorem, that is a subset has n of a denominable set is either finite or denominable. Proof: let we have a set which is denominable, and by definition A is equivalent to n, so we can find the element of A as A is equal to set A1 A2 A3 A4 dash 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 and so on. These are the elements of set A. As we know that A is denominable, so here the function f from n to A is defined as f of k is equal to ak, which is obviously bijective 1 1 and onto. And let B is a subset of A, and if B is equal to empty set, then B is finite. And if B is not equal to empty set, then since B is a subset of A, so we can find an element, say A and 1 belong to A, such that A and 1 belong to B. And if B is equal to A and 1, which is again a finite, but if B is not equal to A and 1, it means that B is not a finite set. Then there is another element, A and 2 belong to A, such that A and 2 belong to B. And if B is equal to A and 1 A and 2 set, then again B is finite, taking two elements. But if B is not equal to A and 1 A and 2, then we can have A and 3 belong to A, such that A and 3 belong to B. And if B is equal to A and 1 A and 2 A and 3, it means that B contains three elements, then B is finite. But if B is not equal to A and 1 A and 2 A and 3, then we continue the above process as such. We have B is equal to A and 1 A and 2 a and 3 and dijudge and so on, where ni belong to z plus set of positive integer, and if indexing set n1 n2 n3 dijudge and so on is bounded, then it is finite, otherwise it is denumerable, because we can find a function, another function g, from n set of natural number to the set b, defined by g of I is equal to a and I, where I belong to set of natural number, then g as defined above is obviously bijective. Thus b is not finite, b is not finite, is denominable. Thus every subset of a denominable set is either finite or denominable. That is our required theorem proved.